Pour yourself a drink. Any drink. Water, whiskey, juice, it doesn't matter. Now drop an ice cube into it. And listen. Crack. You've heard that sound 1,000 times. Everyone has. It's one of the most familiar sounds in the world, and almost nobody has ever stopped to ask the obvious question, why is the ice making noise? Think about it for a second. It's frozen water. It has no moving parts, no motor, no air pockets hissing, nothing mechanical inside it. Nothing in a solid block of ice should be able to produce sound. And yet, the moment it touches your drink, it snaps. Sometimes it pops. Sometimes, if you listen closely, it almost shrieks. Here's the part nobody tells you. That sound is not random, and it is not harmless. It's the sound of the ice cube being violently torn apart from the inside. In the first 2 seconds inside your glass, that little cube experiences forces strong enough to shatter solid material. The same category of stress that cracks engine blocks in winter, bursts water pipes inside walls, and splits mountain rock apart over centuries. All of that happening in miniature, right next to your hand, every single time you make a cold drink. This is the story of thermal shock, a force most people have never heard of, a battle happening in every glass of ice you've ever poured, and the reason scientists are now lowering microphones into the coldest waters on Earth to listen to ice scream. Because that scream is measuring something much, much bigger. But to understand why an ice cube screams, you first need to understand something genuinely strange about the world around you. Something that sounds fake the first time you hear it. Almost nothing you own has a fixed size. Your phone, your windows, the bridge you drove over this morning, the rails a train runs on. All of it is expanding and shrinking constantly as temperatures shift around it. The reason is simple. Heat makes atoms vibrate harder, and vibrating atoms push each other apart. So when an object warms up, it swells. Cool it down, and the atoms calm down and huddle closer together. The object shrinks. The Eiffel Tower is actually measurably taller on a hot summer afternoon than on a freezing winter morning. The metal itself grows. Usually, you never notice any of this. The changes are tiny, and, this is the key word, even. The whole object warms up together, so the whole object grows together. Every part moves in agreement with every other part. No conflict, no drama. Engineers, however, think about this constantly, because they've learned the hard way what happens when they don't. It's why bridges have those metal comb-shaped joints built into the road surface. They're expansion joints, gaps that let the bridge grow in summer without crushing itself. It's why railway tracks are laid with small spaces between sections, because rails that can't expand will buckle and twist like snakes on a hot day. It's why power lines are strung with slack, sagging lower in the heat. The entire built world, everything humans have ever constructed, is quietly designed around one single rule. A solid object can survive changing size. What it cannot survive is changing size unevenly. When one part of an object tries to move and another part refuses, the object doesn't bend, it doesn't negotiate, it breaks. Remember that rule, because that is exactly what you do to an ice cube every single time you make a drink. Here's the timeline of the attack. Your ice cube comes out of the freezer at around minus 18 degrees Celsius. Your drink is sitting on the counter at around plus 20. That's a gap of nearly 40 degrees. And you close that entire gap in a fraction of a second, the instant the cube hits the liquid. The moment it lands, the outer surface of the cube warms up almost immediately. The liquid wraps around it and floods it with heat from every direction at once. And warming ice, right before it melts, wants to expand. Its outer layer gets the signal. Temperature is rising. Spread out. Take up more space. But here's the problem. Only the outside got the message. The core of the cube has no idea anything happened. It's still sitting at freezer temperature, rock hard, frozen solid, completely rigid. Ice is a terrible conductor of heat, so the warmth from your drink crawls inwards slowly, layer by layer. Which means for those first few seconds, you have a shell that is desperately trying to stretch, welded onto a core that refuses to move. The outside pulls. The inside holds. The outside strains harder. The inside doesn't give a millimeter. Stress starts building along invisible fault lines inside the crystal. Enormous stress. The kind engineers measure in tons per square meter, packed into a piece of ice smaller than a matchbox. And here's the cruel detail. Ice is actually strong under pressure. You can squeeze it surprisingly hard. But it is terrible, genuinely pathetic, at being stretched. Pulling ice apart takes only a fraction of the force that crushing it does. So in this tug-of-war between the shell and the core, something has to give. And it does. The cube fractures. A crack rips through the crystal structure at hundreds of meters per second, faster than a passenger jet. And that sudden release of trapped energy slams into the surrounding liquid and air as a pressure wave. That pressure wave is the sound. The crack you hear is, quite literally, the ice breaking, not settling, not melting, breaking. That's why, if you fish the cube out of your glass afterward, you'll find it full of white lines, veins, and fractures that were not there in the freezer. Each one of those lines is a scar from those first violent seconds. Your drink didn't cool the ice gently, it ambushed it. And the crack you heard was the sound of the ice losing. Now, if you've ever noticed that some ice cracks violently and some barely whispers, you're not imagining it. 3 things decide how loud the war gets. First, the temperature gap. A cube from a very cold freezer dropped into a warm drink cracks hard, because the bigger the difference, the bigger the uneven stretch, and the bigger the fracture. Drop ice into room temperature whiskey, and it snaps noticeably louder than in cold water. Bartenders know this sound extremely well. It's the soundtrack of every whiskey pour on the planet. Second, the size of the cube. Bigger cubes scream more. A large cube has a long distance between its warm surface and its frozen core, which means more trapped stress with nowhere to go. Crushed ice, on the other hand, barely makes a sound. The pieces are so small that they warm through almost evenly, all at once. And if the whole piece warms together, there's no conflict and nothing to tear apart. Remember the rule. It's not the temperature change that breaks things. It's the unevenness. Third, what's already hiding inside. Cloudy, homemade ice is full of trapped air bubbles and impurities, thousands of tiny weak points where cracks love to start. That's why freezer ice tends to crackle and fizz with lots of little snaps. Clear bar ice, frozen slowly and evenly, has far fewer flaws. It holds out longer under the stress, and when it finally fails, it often goes with one single dramatic pop instead of a dozen small ones. So that random kitchen sound turns out to be a surprisingly precise physics readout. How cold the ice was, how big it is, how pure it is. You can literally hear the quality of your ice if you know what you're listening to. And this is where the story gets much, much bigger than your glass. Because ice cubes are not the only ice on this planet being dropped into warmer water. In the polar regions, there's a phenomenon sailors have known about for centuries. When chunks of ancient glacier ice break off and fall into the sea, the water around them starts to fizz, crackle, and pop, so loudly that early sailors genuinely believed the ocean itself was making noise around their ships. The sound even has an official name, Bergy seltzer, and it's the exact same physics as your drink, scaled up to the size of buildings, with one extra ingredient. Glacier ice is packed with millions of pressurized air bubbles, ancient air trapped inside the ice for thousands of years, squeezed tighter and tighter by the weight above. When the ice finally melts in the sea, those bubbles don't just leak out. They explode out, one after another, like microscopic gunshots. And at some point, scientists realized something remarkable. If melting ice makes noise, then noise can measure melting. Today, researchers sail into fjords in places like Alaska and Svalbard, lower underwater microphones into the freezing water, and simply listen. The louder and more frequent the crackling, the faster the glacier in front of them is falling apart. Entire studies now track the health of glaciers by sound alone, because the screaming is often easier, cheaper, and safer to measure than the melting itself. And the numbers are staggering. In some fjords, melting glacier ice is among the loudest natural sounds in the entire ocean. Louder than rain on the surface. Loud enough to be heard through instruments from kilometers away. Which means the tiny snap in your glass and the roar of a dying glacier are the same event, playing at two different volumes. Same physics, same tearing, same scream. One of them cools your drink on a Friday evening. The other one is quietly rewriting the coastlines of the planet. So, back to your drink. The next time you drop a cube in and hear that little crack, you'll know exactly what it is. It's not the ice settling. It's not bubbles escaping. It's a solid object being torn apart from within. Because one half of it got the news before the other half did. It's the sound of a 2-second war between a warm shell and a frozen core. The same force that engineers design entire bridges around, the same sound that scientists are recording at the ends of the earth right now to take the temperature of the planet itself. Everything changes size. It just can't do it unevenly. Your ice cube learned that the hard way. And from now on, every time your drink cracks at you, you'll hear it for what it really is. Not a pop, not a fizz, a scream.